Mm. Hello, am I audible? Hello, can anyone answer?
Yes.
Yeah. So let's wait for another 5 minutes, then we can start. So in the meantime, you can introduce yourself. So let me first introduce myself. So I am Sujan Mondal. Uh, I'm the TA of your course. So I'll be taking this live session every Tuesday from 7 to 9 p.m. And I'm currently doing my PhD at here at IIT Bombay. And so with this, I would like to know you. So maybe I can see Deeptonu Das. So can you introduce yourself?
Yeah, hi, I am
Hi.
Deeptanu and I am
Hmm.
a third year BSMS student at IISER Trivandrum
Hmm.
and I am pursuing chemistry as my major.
Okay, okay, okay. So I think there you have already started some research project also, or you're just learning the stuff?
No, we start our major project from eighth semester onwards, like from fourth year.
Oh, 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 I see, I see. Okay, and Malavika Devi. I'm sorry if I'm pronouncing wrong.
Yeah, I'm also from ISET Trivandrum and
Hmm.
I'm a fourth year and
Okay,
I'm also a chemistry major and yeah.
okay, okay, okay. Okay, so we'll start sharply at 7:05. I think that would be fine. So just let's wait for another 2 minutes. Can you see my screen?
Yeah.
Yeah.
So what I'll do is today it will be just kind of introduction to the live session that we'll do. I'll go live on today, and from the next week we can solve more problem. So even in the first week of your class, whatever has been taught, so I'll just briefly summarize those, and then I'll ask you that whether you have any doubts so that you can ask me, and maybe some of the question I'll not be able to answer, but be assured that I may answer that in the next week if I don't know the answer. And then later on, after solving or giving answer to your questions, we can discuss some practice problems. So you can solve and you can interact. So see that this is a live session, and I want you to interact. Otherwise, this will not have any meaning, right? So I'll just briefly summarize um, whatever have been taught in this first week. So as you all know that the only solvable, exactly solvable problems are the one particle problems. For example, your particle in a one-dimensional box, or uh, harmonic oscillation, oscillator, rigid rotor, particle in a two-dimensional box, and etc. etc. Or hydrogen atom, most importantly. But many electron problems are not exactly solvable, right? So can anyone answer that why many electron problems are not exactly solvable? What is the culprit? It's not exactly solvable.
Correlation.
Correlation, what do you mean by correlation?
Like electron repulsion is not easy to quantify when the number of electrons increases.
Yes. So if there is two electrons itself and they are interacting because of the 1 by R12 term in the Hamiltonian, you cannot actually separate out as a you cannot write the Hamiltonian as a additively separable. So I'll come to that. So that's why the many electron problems are not exactly solvable. So we seek for some approximate methods. So that will be eventually taught, I think, which has already been started in our week 2, I guess. And later on, the postulates of quantum mechanics were briefly discussed, where psi is the state for any system, and psi contains all the information. If you take the modular square of the psi, you get the density. And if you take the psi square times if it's a one-dimensional function, psi square dx, then it's the probability between that and all of these things. And then you learned what is the average of any operator. For example, if we take an average of a operator A, it will be psi A psi divided by, if your psi is not normalized, right? And I think you all know that what is Bra and Kate notation. And then it was discussed that you can write any wave function in a complete basis as a linear combination or superposition of all those bases, and the coefficients are the probability, the coefficients modulo square are the probability of finding that particle in that particular state, right? So what do I mean by that? Um, let's just recapitulate whatever has been taught, then we'll discuss some problem. So you can write any psi as a summation of Cn phi n, where this phi n forms a complete basis, right? Then if you observe if you measure some observable on this state psi, then the probability of finding the particle in a particular phi nth state, for example phi 1 or phi 2 state, will be given by c mod square, right? And summation of c mod square is 1. So these are the properties that you have learned. You have also learned that that the eigenvalue of any Hermitian operator is real, and if two operator commutes, then they will share a common set of eigenfunctions and all. Then continuing on that, you have learned that the electronic or fermionic wave function must be antisymmetrized. That means if you have a wave function where this 1 and 2 represents the your uh, coordinates of one and second electron, and if you permute it, like if you change the 1 and 2 coordinates, this will be minus of that. That is actually the antisymmetry, right? And in this respect, Sir has taught that what is Slater determinant. It takes care of the antisymmetrization problem. There was this non-interacting and interacting problem, and there you have seen that in case of non-interacting problem, this product gives you an exact solution. However, for the interacting case, that's just an approximation, and then full CI in a complete basis is exact, but you cannot form a full like complete infinite basis. So there were this full CI in the finite basis, right? So far this has been taught in your first week. Now, do you have any doubts? So then we can go on solving some of the problems. In this week one, do anyone has any doubt?
No.
Okay.
Yep.
Okay. So, so I think this is the problem that was there in your practice quiz or practice assignment. So can anyone answer these questions?
Option four, because
Option
um, four,
4.
linear
And
and non-linear.
why? So what is the like? What are the features or characteristic for an operator to be linear?
Uh, so for linearity, we
Hmm.
know that basically two rules.
Hmm.
It should be homogeneous and basically uh,
You can also tell the
well,
equation itself. That is also fine. So
okay.
for
So if let's say operator A operates on phi
phi.
and it gives lambda as the eigenvalue,
Okay.
and then if we consider uh, like a linear combination of two phi's, like phi 1 plus phi 2,
Okay.
then it would
It will give you.
give it will again give lambda phi 1 plus lambda phi 2. So
So it's like A is operating individually on this function.
yeah,
Yes. And another one.
uh, but however, like in this C phi, it will become yeah C phi C of inside.
Right? So these are the two
Yeah.
properties to be validated whether it's a linear or non-linear operator. So in the
Like
first case,
additivity and homogeneity, if I remember correctly.
yes. So that's what it is. So for example, the second case, this case, it's not uh, linear, right? So let's check that why it's not linear. So it is given that C phi is giving you phi square, right? So this is how the C operator operates on any function. Okay, it returns a square of that wave function. So if C operates on, for example, phi 1 plus phi 2, what will it do? It will do, right? So because this is your whole function, so according to this rule, it will give you this phi1 plus phi2 whole square, right? Now if you break it down, this is phi1 square, phi2 square plus 2 phi1 phi2, right? But if this C was a linear operator, what we should have got? So if this was a linear operator, then we should have got C phi 1 plus C phi 2, which should have given phi 1 square plus phi 2 square. But clearly these two are not equal because of this term. So that's why this is a non-linear operator. So the fourth option is correct answer, right? Now, is it visible to everyone?
Yes.
So you can take 5 minutes to solve this problem. Can anyone then answer this question? So let me explain. So in this case, what you have given, you have an operator B and you have a function capital F, which is giving you the eigenvalue S and the eigenfunction F. And the same operator is operating on another function G and giving you back the same eigenvalue. That's why these G and F are the degenerate solution of your B operator. Now I am writing a function g1 which is actually f and g2 as a linear combination of g plus cf. So can then I want this g and g2 to be orthonormal. That's why I'm writing that it is equal to 0. Then can you determine that what is the value of c? So anyone has any answer?
Option 3.
Option?
3.
Okay, someone is saying that the option 3 is the correct answer. Is there any other option, any answer?
Yeah, I also think it's option 3.
Okay. So you both are saying that it is the option third. So how did you approach the problem? Am I
Just
audible? Hello?
using
Yes.
the orthogonality condition.
Yes. So you are given that G1, G2 is equal to 0, right? Now if you put F and G plus CF, that should give you 0, right? Now you have F times G and C times F, F, and that is equal to 0. Now this FF, this is equal to 1 because it is normalized. Like if it is given that it is normalized, then you can put it 1, and if it's not given, then you can keep it there, and because the normalization is not a big deal, so you will get C is equal to minus of Fg. So this is the correct answer. Do you know what is this called? This is called Gram-Schmidt. I might be wrong in the Gram-Schmidt orthogonalization. The spelling you check, but this is called Gram-Schmidt orthogonalization. So what actually we're doing here, so I think from the postulate you know that the eigen functions of an operator, and if they produce two different eigenvalue, then the wave functions are orthonormal to each other. But here you see it shares the same eigenvalue, right? Then you cannot say that whether these F and G are orthonormal or not, right? So do you guys know this theorem, or should I prove?
Yes, we learned it.
Okay, so then in that case you can take a linear combination, and another thing is that if you take linear combination of two function which has the same eigenvalue, then this linear combination will also give you the same eigenvalue itself, right? So in this case, so you have taken this G plus CF, or you can normalize it back, then you will get this C, which will fulfill this orthonormality condition. Now the next problem, this. Can anyone answer?
It's like instead of considering electron-electron repulsion as like the Coulomb potential of like 1 by r, they you consider that each electron fields and potential like an average field of the rest of the electrons in the system, and so it doesn't neglect inter-electronic repulsion. It just like approximates it as like a field, like as one potential, instead of considering it separately for each electron pair.
Yes, you're partially correct. Let me explain. So the orbital approximation is essentially, if you have a n particle system, then your wave function is will be n coordinate, right? So maybe 1, 2, and dot 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 up to n. So you can approximate with the wave function as a summation, as a product of an one particle wave function, for example, phi 11, phi 22, phi 33, like this up to phi n. So this is the, you can approximate the full wave function as a product of the one particle wave function. But does it involve like negligence of the inter-electronic repulsion? The answer is no. Like why? So your Hamiltonian contains this cut square by this summation of, then you have this I1 to n, and you have this Rij terms, right? Now, if you neglect this term, which is the basically the interaction between the electron, if you neglect this term, that means you put it this equal to 0. That means there is no repulsion between the two electrons. So it's kind of a non-interacting system. And as you all know that for a for a non-interacting system, so you can write the Hamiltonian as a summation of the one electronic system, right? So in this case, you can write the wave function which is exact as the product of phi 1, 1, phi 2, 2, dot up to phi n. So in this case, this is exact because they are not non-interacting. But this is called approximation because you don't know the exact solution, but you are approximating that yes, this might be a like good choice for my wave function, this total psi. So here we are not neglecting this inter-electronic repulsion. If you neglect it, then you have the exact solution. The approximation what is coming from that you still have the inter-electronic repulsion, but you are considering is an approximation to the exact wave function. So this is again one of the problem for your from your week 0 assignment. This is very simple, right? Which is the answer? What is the answer?
The third one.
This one, right? And why the third one is the answer? Why do you
The
think?
total wave function has to be antisymmetric. So if the spin part, if the spatial part is symmetric, the spin part has to be antisymmetric.
Okay, so here the spatial part is symmetric, so that's why you are choosing this spin function as an antisymmetric. So can you categorize the first option, the alpha 1 and beta 2 and alpha 2 beta 1 as symmetric and non-symmetric one? Can you tell whether the first one is symmetric or antisymmetric? Sorry?
I think it's symmetric, but depends on the spatial part also.
So you are saying that this alpha 1 beta 2 is symmetric.
Yeah.
Any answer
The
to
spin
that?
part is symmetric.
No, so see, for the total wave function has to be antisymmetric, right? So
Yeah.
you can also categorize the spatial part and the spin part as like So if your special part is symmetric, you will choose your spin part as an antisymmetric. If your spin part is symmetric, you will choose your part as antisymmetric. So you can categorize the spin part itself as symmetric and antisymmetric. So you said that this alpha 1 beta 2 is symmetric, right? But if you
Yeah.
see, so for what is the definition of a symmetric one? So this for any function which is a function of 1 2, it's symmetric if you operate a permutation operator p1 2, and if it's give you back the same expression, then it's symmetric, right? So let's say
Yeah.
if I operate this permutation operator p1 2 on this spin function, it will give me alpha 2 beta 1, right? So
Yeah.
can you say that this alpha 2 beta 1 is equal to this alpha 1 beta 2?
No.
You cannot say, right? So you
No.
cannot categorize. So that's what my question was. This alpha 2 beta 1, you cannot categorize these two wave function as symmetric or antisymmetric. So they never take part in your in the spin part. You have to take a linear combination of these to make it symmetric or antisymmetric. So the answer is you cannot categorize this individually, this alpha 1 and beta 2. However, there is this alpha 1, alpha 2 and beta 1, beta 2. You can easily categorize them to be symmetric, right? Then I think again, this is a simple question. So what will be the answer?
Six.
Okay. So can you tell me how did you solve this question?
So the only way, since it's a 3D box, it has to be nx square plus ny square plus nz square equal
What are
to
these
14.
nx, ny, and nz?
It's the level in the x direction, y direction, z
The,
direction, like the
they're the quantum number.
the quantum number.
Yes.
And it so the only way it can be 14 is if it's nx is 1, like the nx ny nz is either like 1 2 3. So if you take all of the permutations, you will get 6 as the answer.
Yes. So for a three-dimensional cubic box of length L, right? So can you tell me the what will be the form of the wave function? Though it's not necessary for this question to be solved, but I'll again tell that how does this degeneration is coming from, right? So your total wave function nx, ny, nz is basically root over of 2l cube sine nx by x by l sine ny by y by l sine nz by z by l, right? And you can write the energy as nx square ny square nz square h square by 8ml square, right? So as she mentioned that you are given that this nx square plus n square plus nz square is equal to 14. The only way it is possible that this nx, ny or nz to be 1, 2, 3 or the other combination. But so why they are called degenerate? So if you take this combination as 1, 2, 3, or let's say 2, 1, 3, or you have let's say 1, 3, 2, then 2, 1, 3, we have 2, 3, 1, 3, 2, 1, and 3, 1, 2. So these are the 6 combination that is possible, and you can see these 6 combination will give me different state, and that can be seen from this wave function, but they share the same energy, or they give you the same eigenvalue. That's why they are called degenerate, and in this case you can get 6 degenerate states, so that's why the answer is 6. Now so this is very trivial, but can anyone prove that why this Cn square is the answer that you are going to give? What is the answer?
One.
Okay. So how will you prove that whether this summation over n Cn mod square is equal to 1? Anyone can prove that how to prove this Cn mod square summation is equal to 1? Can anyone tell me what is projection operator? So let's say you are representing any wave function in a orthonormal basis, which is Cn phi n, right? So this phi n psi, is this a operator? This quantity phi n psi is a operator or not?
Mm, no. This is the inner product.
This is the inner product, and what will it give you?
It will be just Cn.
And yes, so what is this Cn called? So you are saying that it will give you Cn. So this actually gives you the projection of psi along the phi n basis, right? So this will give you just a number. So this is not an operator, but and whether this is an operator or not, what is the definition of an operator?
Yeah, it is an operator.
And why do you say that? Why do you say that it's an operator?
It will give a square matrix like this is an outer product. It will give a square matrix as and which is how operators are written.
So this is the basis, right? If you write any operator in that basis, that will give you a square matrix. That is fine. Even you can write this operator in another basis, that will give you a square matrix, that I understand. But from a very general point of view, without going into this matrix algebra, can you tell that like why we call this as an operator, not a number or not anything else, but it's an operator?
I'm not sure exactly.
Okay. So what is the definition of any operator? So any operator, let's say A. Operator, the definition of operator is that it operates on any function f and will give you back another function or maybe the same function, and depending upon its functionality. That's an operator. So if it's operate on function, it will return you an function. That is the definition of any operator, right? So let's say if this operates on any function, let's say psi, then let's operate it on phi and psi. Even if we don't know that whether like what is this phi n or psi, this is we know that this is an number because this is an inner product, and number times a coefficient times a function is actually a function back. So this is an operator because if it's if it operates on an operator, it is giving you back some function. That's why it is called an operator. Now so it is called an projection operator. So do you know that why it's called projection operator? Why is this naming?
Like if you act this on some wave function, it gives you the projection of the wave function on that basis.
Yes, along that basis, right? So what she meant is that, so let's say it is any phi I and phi I. If it is operating on our this function psi, so it will give you, so this phi I psi is basically ci, right? And you have phi I, and which is the projection of the psi along the basis vector phi I. That's why it is called an projection operator. Now, a very important property about the projection operator is that if you take the summation of all these projection operator, phi I, this is an identity operator. Can anyone prove? This is a very frequent characteristic of the operator that you are going to use in your due course. It's a very frequent relation that is being applied in all over the quantum chemistry problem. Okay, let me show you. This is very simple, but still, I'll show you how to prove it. So, what an identity operator do to any function? If this is an identity operator, if it's operates on psi, it will keep it unchanged, right? So it will give you back the same function. So if we can prove that, if we operate this projection, the summation of this phi I outer product on any function, and if it returns the same function back, then we can definitely say that this is an identity operator. So let's operate this fellow on to this psi. So you have I, phi I, phi I, and you have psi. So you are operating this on the function psi. This is very simple. And what is this phi I psi?
Ci.
Ci. So you are actually getting Ci phi I. And I is a dummy index. You can replace it with anything you want. So we have defined like with n. So we'll just denote it with the n itself. It doesn't matter though. So this is actually giving you the same wave function back. That's why this is called resolution of identity. Resolution of identity. Please remember this relation. This will be very helpful. Now coming back to the question. So can you prove that now can you prove that this summation of n sin square will be equal to 1? Anyone?
Like, I was thinking
Mm-hmm.
if we just take that the inner product of psi with psi is 1, and we take psi as like the summation over n cn phi n, and
Mm-hmm.
another the ket psi as like summation m cn cm phi m. And if we solve that, we'll end up getting um, like cn star, like summation of cn star cn is equal
Mm-hmm.
to 1, and hence
But how you
like
are getting the 1?
like we start with the saying that the inner product of psi with itself will be 1.
That's you are going in the right direction. So you can see in the question it is written the psi is normalized. So you don't have to assume. It is 1. You are going in the right direction now.
And we know that psi is summation cn phi n, so you substitute that into the inner product.
Yes. But my question is whether you will the both bra and kate psi you will express in the same basis, like
No, in different basis.
different basis mean you will put the
Like,
like you will expand in the same basis, but you will
sorry,
give
in
a
the same
different dummy
basis with
variable.
different dummy variable. Yes, yes.
Yes. So yes, that's the actually the proof. So I'll show you. So she is absolutely right. So it is giving that like given that this psi is normalized, right? So that is equal to 1. Now you can replace this brass I as summation of, let's say, some m cm sorry So your psi is some Cn phi n, right? So you can write the bra psi as summation of n Cn star phi n. Anyone has any doubt in this line? Okay. So if not, then I can write this as Cm star. So now you have phi m here, and now you are expanding this right one, this Kate psi in another, like in the same basis but with a different dummy indices. So now you have phi n, now you have Cn is equal to 1. Now we can write Cm star Cn, and what is this phi m phi n? If you see this line, there the orthonormal set. So what will be phi m phi n?
Like Dirac delta phi, like mn. So
Kronecker
it will
delta.
be, sorry, Kronecker
Yes.
delta.
So it will be Kronecker delta. So that is equal to 1. So the term will only survive. So if m, so what is Kronecker delta? Mn is equal to 0 if m not equal to n, and equal to 1 if mn, like m is equal to 1. So the term will only survive if your m is equal to n. So this is very clear now. Cm star, sorry, Cm is equal to 1 n square is equal to 1. So it is proved. Now this question, I think again this is very trivial. So what is the answer?
Like it can be plus or minus one. Like it's a combination of plus and minus ones.
So you will take both -1 and +1.
No, like I guess undefined, because it's not a unique number.
Yes, the answer is it is undefined because your so this is a recapitulation of your exactly solvable hydrogenic part, where the phi solution, the solution of the phi looks like e to the power plus minus em phi, right? Now this magnetic quantum number, so if this m is equal to +1 or -1, you actually get a imaginary wave function. But to get rid of this imaginary number, we can take the linear combination of this. So we can take, instead of m, you have 1, right, for the px orbitals, and sorry, for the p orbitals. So you have this e to the power I phi and p to the power minus I phi. So remember, for hydrogenic system, your energy is only a function of n, right? It doesn't depend on your L value, ML value, anything. So for, if the energy only depends on n, so for both these +1 and -1, your energy is same. So again, the same technique that we have discussed before, that you can take a linear combination of these two, which will give you the same eigenvalue. So what do I mean by that? So let me quickly explain that. So let's say you have an operator H, and if it's operate on phi, if it's giving you energy 1 and phi, and if this h is operating on any other function, let's say chi, and it's giving you back the same eigenvalue, so this we can say this phi and chi are degenerate state. Now if you take any linear combination of this phi and chi, let's say we are forming an wave function which is c1 phi 1 and c2 chi, not 1, this c1 phi and c2 chi. Now if you operate this h on psi, so here your h is a linear operator, you know, so it will operate on this phi, which will give you c1 e1 phi plus c2 e1 chi. So you can take the e1 common and you have c1 phi plus c2 chi. So which is actually giving you e1 psi. So your h psi is equal to e1 psi. So see, with taking this linear combination of two degenerate solution will give you the same eigenvalue when you operate that operator on that function. So with the same thing, we are actually taking the linear combination of e to the power I phi and e to the power minus I phi, and you can see that when you take the linear combination, then you cannot define the magnetic quantum number of that orbital. So in the px orbital or py orbital, we cannot define. But then what about the pz orbital? What is the magnetic quantum number of pz orbital?
It'll be 0.
Yes. I will request the other people who are there in this meeting. You can also answer. Sumon, I can see Sumon. Can you introduce yourself? Like I haven't talked with you. I have talked with Diptonu and Malvika. Sumon, where are you from? Are you there? Yeah, hi, hi. Uh, where are you from and in which I am from? Yes, okay. So you can interact, there is no problem. You can turn on your mic if you have. So in the very beginning of this session, I have told that if you have any doubt so far in the session that you haven't understood any particular topic or any particular equation or anything, you can just let me know. I'll try to cover those. Okay, it seems that everything is fine. Okay, so here it is not defined, and I think you know that why it's called a px orbital and why the other one is like other linear combination is pure orbital. I'm not going into that. So it's basically that you can transform your r theta phi coordinate, like when you take the linear combination and then when you transform back to the your Euclidean coordinate, that is xyz, you'll see that um, yeah, okay, that's fine, that's fine. So then you will get that x is equal the x coordinate, and when you take the other combination, then you get actually the y coordinate there. So that's why it is called a px and py. Now, so this is a very important question. let's first answer the first part. Like why are two electron spin function alpha 1 beta 2 and beta 1 alpha 2 not acceptable? Anyone wants to answer?
You told that like it's neither symmetric nor antisymmetric.
Yes, yes,
So
that's
we
an
can't make the total wave function antisymmetric if we use those.
yes, that's so true, and that is one of the answer. But can you like intuitively tell that way why these spin functions are not acceptable? Like, what is the physical significance of that? Can you think it of from physical point of view? Anyone? Diptonu, are you there?
Yes, sir.
Can you answer like why this is not acceptable? You and she was right that it's neither symmetric or anti-symmetric, so it will not fit into any category, so you cannot use them. Uh,
Uh, because electrons are indistinguishable, first of all,
mhm.
and
So how is it violate like is it violating the indistinguishability?
no, this I think the wave function is valid.
You are talking of the second question
Mhm.
or the first one? I'm
Uh,
only focusing on the first part that why are two electron spin function are not accepted.
okay.
So you are saying that it's not okay. So let me answer that. Um, like yes, you are absolutely right that it's neither symmetric or anti-symmetric, so it's not acceptable. That is a fair answer. That is a fair answer. But if you see this when you write alpha 1 beta 2 as a function, so you are pointing out, hey, electron 1, you have alpha spin, and hey, electron 2, you have beta spin. So in when you write this as a wave function, like in spin function, see you can actually distinguish two electron. So you can say, okay, I can see the one electron, the first electron has alpha spin and the second electron has beta spin. So you are violating the principle that they are indistinguishable. So that's why you can answer in that way also. So you are pinpointing that I can distinguish between two electrons. So that's why it's not acceptable. So you have to linear combination, and in case of linear combination, you don't know exactly which electron has which spin, right? So that's another answer that is usually given. So now, coming back to the second question, the second part of this question, consider the following Slater determinant for a two electronic system. Comment whether this is a valid wave function for helium atom in one of its excited states. So, so can anyone comment?
I think the wave function is valid because it changes time on interchanging the coordinates.
So you are saying that it is antisymmetric, that's why it is valid.
Yeah.
Any other answer? Anyone? Okay. Let's see whether this is valid or not. So your psi is, so I'm not writing the constant part. So let's break it down. So you have 2s1 alpha 1 times 3s2 beta 2 minus 3s1 beta 1 2s2 alpha 2. So now if you change the 1 and 2 electron, you can see that it's antisymmetry. So you will say uh, it is valid. But there is an interesting fact that let's write the configuration in the orbital diagram. Let's say you have a 2s level here, you have a 3s level here. So what it is saying that the first electron, the 2s, has alpha spin, whether the second electron has beta spin, right? And you are taking a linear combination of this uh, configuration where the again it has a beta electron, sorry, beta spin, and it has an alpha spin, right? So by drawing this diagram, you can actually see that you are taking, like you are considering the same configurations. So you are saying that the electron which is there in the 2s orbital, it's actually has up spin. So from here, so again you are violating the indistinguishability here, that you are saying that whatever the electron is there in the 2s orbital, it has a alpha spin, and whatever the electron is there in the 3s orbital, it has a beta spin, which is not right. So if we have to write the correct linear combination, so you all know for this combination you will take linear combination which actually looks like this. This has the same energy, and this is the correct linear combination to take. So this is not the correct. So this is not the valid wave function in one of this excited state. Because if you draw these two excited configurations, so then you are actually pointing out that they are distinguishable, but they are not. So to make it right, you should have taken this linear combination, not this one. Okay, so this is not valid.
So the total wave function is still like antisymmetric because it's coming from a Slater determinant, but just
Mhm.
that it physically doesn't make sense, so it's
Mhm.
not valid.
Yes,
Okay.
yes. Now, this is a very easy question for you. So, what will be the answer?
Could you once go back to the previous question? Like, if we take that particular linear combination, how is that making it? How is that satisfying the criteria? Like,
So, in this case, you are not pinpointing that whether the two electron is alpha spin or beta spin. So, here you are taking the correct linear combination of this configuration and this configuration, which will make you this is an correct excited state determinant, not the one that I have given in the question. Okay.
so the expression of the determinant will remain the same, or
Okay, so you are talking about the how the expression will look like, right? So in that
Yeah.
case, to write the Slater determinant, okay, so how the Slater determinant will look like? So 2s1 and yes, so in that case you have to, so what I'm saying is that this is one of the possible, what I'm trying to is that say is that, so here you have 2s beta and this is 3s alpha. So you will write a Slater determinant psi. I should not write psi, but I'm not writing again the constant, that is 1 by root over of 2. So you will have these 2s 2s beta, or write 2s beta, then you have 3s alpha, 3s alpha, then you put the electron. So here you will put 1 2 1 2, right? So you have to take the linear combination of this letter determinant and this letter determinant, then it will make like the correct description of the excited state. This alone, as a Slater determinant, this is fine. Like, are you getting my question? When you yes. So for the excited state, this is one of the determinant, but you have to take the linear combination of this determinant and this determinant to make it right. So then you will not say that whether this is a like you cannot separate out the electrons, like you cannot distinguish the electron in that case. So again here, if you take the linear combination, so what is actually you are getting this configuration minus this. Then if you take the linear combination of this, and again you will get a again this, it will be a minus and plus
Okay.
12
So
beta.
one term just gets added to the. So
Yes.
there are two determinants.
Yeah, there are two determinants for this excited state. Like for the particular
And
this configuration.
how
Yes.
it helps the indistinguishability? Can you just once repeat it?
So when you take the linear combination of all these configurations, so now you cannot say that the whatever the electron that is present in the 2s has alpha spin, or you cannot pinpoint that whatever the electron is there in the 3s orbital, it has a beta spin. You see, you have taken all the linear combinations.
Okay.
Is it clear?
Yeah.
Okay. And this is very trivial. I think you have already the answer.
56.
56, right? I think you have calculated with 8C3,
Six.
right? So, what actually we'll be doing in this course is that, see, the story goes like this. For the non-interacting case, if you have the solution for the one particle solution, you can take a Slater determinant, properly antisymmetric Slater determinant, and that Slater determinant is exact for the state. So if you take the different Slater determinant, it will give you different state depending on ground state and excited state, and they are exact. Now, when you include, or actually in the real case there is electronegative repulsion, and you cannot separate out this 1 by r(2) as a additively separable term. So you cannot have a exact wave function. So I think in the lecture 6 or lecture 7, it was shown that there remains a form of the exact wave function. What the exact wave function is that if you take the linear combination, so the how the exact solution looks like, if you take the linear combination of all the Slater determinants, right, I to infinity. So if you have you have a infinite basis set, and in that basis set you will get infinite Slater determinants. If you take the linear combination of all those determinants, then your solution is exact. But the the uh, the problem is you will never have a infinite basis set. You will deal with a finite basis set. Okay. Uh, so I think. Do you know any name of the basis sets? So there are different hierarchy of the basis sets. For example, STO3G, 631G, CCPB, DZ, TZ, 4Z, 5Z. So this actually it's a large basis set that you are going. So even if they are finite basis set. Okay, so within this finite basis set, you will have a huge number of determinants. That is called a full CI within that basis set. Even doing a full CI is not actually possible, right? So then, so there are two level of truncation. So the first level is that you have a finite basis set, and the second level of truncation is that you are actually mm, you are actually truncating the subspace, like the determinants. What do I mean by that? So let's say let me show you diagrammatically, right? So So let's say above these one are your virtual orbitals, which are not filled, right? And these are the orbitals which are filled, right? And this is one of the determinant. So you can write the determinant because you have the phi 1, phi 2, and up to then let's say phi n. Then you can write the antisymmetrized Slater determinant for this. So from this determinant, now you can generate different kind of determinants. Let's say single excitation. What do I mean by single excitation? Let's say we'll excite only one electron. So let's say we'll excite this electron. So all this electron was filled, right? Because I have denoted this line. So let's say I am exciting this electron here. So so now you have all filled electrons, but there is one electron that is been already excited. You can generate another one here, or you can excite from core also. Core means like deep down to this orbital. So these are filled. So now you are exciting from here. It can go here. So there are numerous possibilities. So this is called a single excitation. Now you can have also double excitation. So these are single excitation. You can have also double excitation. So what do I mean by double excitation? Let's say there are two electrons, both of them are excited. One is sitting here, another is sitting here, or let's say one is here, another is here, and now you are exciting one electron from here and another electron from let's say here. So these are two field. So this is called double excitation. Then you have triple excitation. You have like quadruple excitation. So how many excitation can you have? Let's say you have n electron. So what is the maximum number of excitation you can have? Let's say you have a water molecule, right? So how many electrons are there in a water molecule? One water molecule. How many number of electrons?
Mhm.
10, right?
Mhm.
So sorry,
Then
10. So from with these 10 number of electrons, you can generate, so you can excite only one electron, right, to the virtual space. You can excite two electrons at one time. You can excite three electrons. So at most, how many electrons you can excite? So within in any basis set, now if you have your single excitations, double excitation, triple excitation, dot dot dot, up to number of excitation if it is 10, then you have taken all the configuration. Then you have within that basis set limit, that is called a full CI. But it is not actually possible. So generally people truncate in doubles, singles, doubles, triples. So then based on that, you will have a truncated level of CISD, right? So then the question is, within this all can we select only one determinant which will be very important and which will give you the basic chemical sense? So that means uh, if I have n electron and if I have like n orbitals and one electron is sitting any one spin orbital, then is there a determinant which is very important? And that is the answer lies within the Hartree-Fock theory. So that gives you the best determinant out of all these determinants. And using these determinant, you can generate the correlation by adding singles, doubles, and triples, and so on. So the more number of determinants you will add, the cost will increase, right? So this is actually the goal of this course. So I think now you will be taught Hartree-Fock theory, and then actually Hartree-Fock theory you will see there is no correlation. Then for the correlation treatment, I think it will be taught what is many body perturbation theory. So you will see in the first order there is no correlation. Then molar placid perturbation theory it will be taught, and which is very important. And then you will see that in the second order the correlation energy will come, right? Then you will be taught the, I think, configuration interaction in a very slight detail. Then the state of the art, which is called the couple cluster, singles, doubles, perturbated triple, like CCSD parenthesis T. So I think everything will be covered. So yes. Um, so anyone has any doubt uh, till now?
No.
Oh, okay. So any other?
I have one question. Like in the magnetic quantum number question,
Mhm. Mm.
so for PZ we can say that the value of ML is zero.
Yes, you can.
So can we prove it? Like why for so does it come from the angular moment?
So if you
Like
operate on the PZ orbital,
LZ
if
upper.
you yes, if you operate the LZ operator, you will get like MH cross, right, which will be zero. So it will actually give you zero. So that's why it's an eigenfunction of your LZ operator. But if you operate the LZ operator on the px orbital, you'll not like this is not an eigenfunction of you the LZ operator. So that's why you cannot define.
But we can operate the L operator on Px and Py.
You can
L
operate.
square, sorry.
L square
Yeah, L square.
operator.
But L square does not give the magnetic quantum number.
No, no, no. There I think you will get root over of L, no, sorry, L plus L times L plus 1 H cross square, I guess. So that will be there, but yes, for to get the ML value, you have to operate with LZ. So L square and LZ commute, and uh, yes. Any other doubt?
Mm.
Okay, so I think then we can end it in the session here, and maybe in the next week. So there is a Google forum there, I think, in the Google group. So you post your doubt. So maybe you will be seeing a lecture today, and you have some doubt, and you thought that okay, I'll ask maybe in this session. Then you could have like forgot, right? You could have forgotten. But what you can do in that Google Form, you can post the question on that day itself. So it will be posted there. I'll see, and I'll try to clarify. So as you go along with the course, you see the videos, and you try to answer the question. Like you have any doubt, you just post it there, and then it will be very easier for you, right?
So by Google Forum, you meaning the email ID of through which you are getting the details, or
No, there is a Google group. I like there is a one Google group is there, I think, where you can post your doubt in the main page itself. So let me see. Uh, now I cannot access it here now, but uh, anyone knows that how to get the Google, because I have seen that it is there. Anyone has the answer right now? Because I don't remember. Uh, if you have any doubt, you can also email them. So there is I can assure that there is a portal is or Google group is there where you can post your doubt, right? And which is visible to the course instructors itself. Even they can also answer there, right? Okay, then I'll again see you on the next Tuesday. Thank you.
Thank you.